Okay, so let's get started. So last lecture we said that in the next 2-3 lectures we are going to look at PN junction diodes, and as I explained earlier, the focus is going to be PN junction diodes from a terminal perspective, knowing how PN junction diode behaves in terms of its current voltage or capacitance voltage characteristics. And so let's start. In order to understand PN junction diodes, you need a little bit of background on semiconductors, which most of you may already have. So I'll just refresh your memory here. So as I was telling you in the last lecture, we all know that atoms, if I look at an atom, the energy levels in an atom are discrete. What you see over here, different 1s, 2s, 2p and all that. And when you make a crystal, like silicon crystal on which PN junction diodes and other semiconductor devices are made, what happens is when you make a crystal, each one of these discrete energy levels broadens into a band. And so corresponding to 1s, you will have a band here. Corresponding to 2s, you'll have a band. And as these energy levels expand into bands, what happens is the energy levels mix also. So the band structure is pretty complicated. But if we examine the bands, what would happen is you'll see that silicon, for example, will have a series of bands. And some of the bands will be completely full. Just as, for example, 1s level here is completely full. It cannot accommodate more than 2 electrons. So similarly, if this 1s level is expanding into a band like this, then every silicon atom, let's say, is contributing 2 electrons and the band will also be full. So what you have is series of bands that you see here. And you have bands which are full, for example, a band which is completely full and all that here. And then, at least in semiconductors, what you see here is a series of bands which are full. And then after that, you see a series of bands which are empty. That's the nature of semiconductors. So completely full right up till here, and then completely empty afterwards. And that is the picture at 0 degrees Celsius, when there's not enough thermal energy. Okay, that's the picture here. And as I explained in the last lecture, what happens is there's a band here which is full of electrons, but that band does not contribute to current. When it's completely full, the band does not contribute to current because there's no place for electrons to go. In order for current to flow, electrons have to gain energy from the field, and there is no space for that. Okay, so a band which is completely full does not conduct electricity. So as far as semiconductors are concerned, a band like this is useless. It doesn't contribute to any current here. Similarly, this band does not contribute to any current here. The bands that are of interest in semiconductor is the topmost filled band, which we call as the valence band, and the band right after that, which is completely empty, is called the conduction band. These are the two bands that are of interest to us in semiconductors. So as I explained, so the valence and the conduction band are important for us, and we denote it by these two levels here, EV and EC here. EV denotes the top of the valence band, and EC denotes the bottom of the conduction band. And the separation between the two is what we call as band gap. And for silicon, the band gap is 1.12 electron volts here. So that's the picture, let's say at 0 degree Kelvin. Now what happens is, at room temperature, some of the electrons from here, from the valence band, they gain enough energy from the thermal field, and they're able to surmount this barrier here, 1.12 band gap, and they're able to go to the conduction band. So when that happens, what you get is an electron in the conduction band, and you get a vacant space in the valence band, which we call as a hole. So what you end up is getting, so depending on the temperature at which we are looking at, we'll have a number of electrons in the conduction band, and we'll have a number of holes in the valence band here. So these electrons in the conduction band, now conduction band is mostly empty. There are only a few electrons that have come from the valence band, and these electrons, when you apply a field, these electrons can move and can conduct current. So that's one source of current, which we call as electrons in the conduction band. So whenever we talk about electrons in a semiconductor conducting current, we are talking about electrons in the conduction band here. And now, because there are vacant spaces here, the valence band, the electrons in the valence band can also conduct current. Okay, and however, we don't talk about current in terms of electrons in valence band. Is equivalent to talking about current in terms of holes in the valence band. Okay, I'll not go into the details how the net movement of electrons in the valence band can be modeled in terms of net movement of holes in the valence band. Here, so the two are complementary. Okay, so we talk about holes in the valence band and we talk about electrons in the conduction band. The concentration of holes in the conduction band, we call it as N. The concentration of holes in the valence band, we call it as P. And we can see that N has to be equal to P because the source of electrons here is nothing but one electron from here went over here, and that's how you got an electron. So for every electron that you get, you also get a hole, and therefore N is equal to Pi. And we have a specific name for it. We call it the intrinsic carrier concentration. I call it intrinsic because my semiconductor is pure. I've not added anything to it. Okay, so it's an intrinsic semiconductor, and the number of electrons and holes in an intrinsic semiconductor, pure semiconductor, is what we call as Ni, intrinsic carrier concentration. So the units are, as you can see, per centimeter cube. And this is the density of electrons and holes that you get here in silicon, 1.45 into 10 to the power 10, and T equal to 300 Kelvin here. Okay, so that's the density of electrons and holes. And you can see here the density of electrons and holes has to be temperature dependent because we said that's the source of electrons and holes. Electrons are going from here to here. And therefore, you find Ni, intrinsic carrier concentration, depends significantly on the temperature and depends on the energy gap. The larger the energy gap, the less the number of electrons. Then lesser number are able to go to the conduction band, and you get lesser number here. So intrinsic carrier concentration, Ni, depends on the energy gap, depends on the temperature, and you get a certain number of electrons in this. Okay, so that's the picture of intrinsic semiconductor. So remember, whenever we talk about current and we say electrons are conducting current, we mean these electrons in the conduction band. And when we say holes are conducting, we talk about holes in the valence band here. All right, so that's the carrier concentration. Now, when I take a piece of semiconductor, let's say I apply a voltage here, and so this end is ground, and I apply a voltage here, a current flows in the semiconductor. A pure semiconductor is simply a resistor. Okay, it's simply a resistor. If you were to measure IV characteristics, you'll find I versus V. It obeys Ohm's law. I equal to V by R, and R, as all of you know, depends on resistivity or conductivity, L by W. Conductivity now this is the expression for conductivity. Conductivity depends on Q, the charge that each electron and hole carries. It obviously depends on the amount of electrons and holes which are there, Ni, and it depends on another parameter which we call as mobility. How fast the electrons and holes move in response to electric field. So it depends on mu n and mu p. These are the mobilities of electrons and holes. And so if we know what is Ni, mobilities of electrons and holes can be measured in silicon, and Q, of course, is the charge. So if we plug in all the numbers, we get a resistivity of around 2 times 10 to the power 5 ohms centimeter here. So it's a pretty resistive a pure semiconductor is. Okay, the amount of current that you can calculate will be pretty small here because of the high resistivity. That's a pure silicon. Okay. Now, pure silicon is seldom used. There are places where you do use, but for example, for a PN junction, bipolar, MOSFET, what we do is we modify the semiconductor and by adding impurities to it, and we call this process as doping. Now, I've shown here an example of a doping where we have a silicon lattice here, and we have taken silicon out. We have displaced the silicon by an arsenic atom here. And arsenic, as all of you know, belongs to group 5. Arsenic has 1 extra electron as compared to silicon, which belongs to group 4. So what happens is that when you add these donor atoms, we call it donor. What happens is the arsenic donates an electron. This electron that you see here, the extra electron, is loosely bound, and it goes to the conduction band. Okay. So when you add an arsenic, what does it do? It creates a electron in the conduction band. Each arsenic atom, at least at room temperature, creates an electron in the conduction band here. So this is what is happening here. The donors, these are called donors because they're donating electron to the silicon lattice here. So Nd goes to Nd plus. So the arsenic atom or the donor atom will become positively charged and will create an electron in the conduction band. Now note, in this process, the holes are not created. The holes are not created because the source of the electrons are the donor atoms here. So all you are doing is you're taking a donor atom, it gets ionized, becomes positively charged, and creates an electron in the conduction band here. All right, so that's the picture that we have. Donor atom, of course, is large. Arsenic atom is large, is positively charged. It cannot move. It's immobile. What moves is the electron that goes into the conduction band here. And a semiconductor in which we have added these donor impurities. And what happens in such a semiconductor? The number of electrons become larger than number of holes. Because remember, donor atoms are creating electrons. You're not creating holes. So the electrons become much larger than number of holes. And we call such a semiconductor as N-type, where number of electrons is larger than number of holes here. Okay. And so this is the picture that we have here, simplified picture. Suppose I add, this is a typical doping density. So the whole process is called doping. So suppose I add 10 to the power 16 per centimeter cube number of dopant atoms. Then what happens is number of electrons approximately become equal to the number of donor atoms here. Because remember, intrinsic carrier concentration was how much? 10 to the power 10. So when you add 10 to the power 16, the number of electrons will be equal to 10 to the power 16. The intrinsic carrier concentration will not have an impact because that was very low. So N becomes 10 to the power 16. And then we have this relationship in semiconductor that in equilibrium, the product of electrons and holes is always equal to Ni square. Don't ask me for proofs here, but so the important point is in equilibrium, the product of electrons and holes is always equal to Ni square. So what happens is when you increase the number of electrons to 10 to the power 16, the number of holes, they reduce. The number of holes become 2 times 10 to the power 4. And so we know that number of electrons is 10 to the power 16, number of holes is 2 times approximately 10 to the power 4. The product is equal to Ni square. Okay. Now one process that I forgot to mention for you is I told you about a process where an electron from here can go over here and therefore you get a free electron in a hole. Now you can also imagine that an electron from here can fall into a hole here and thereby the electron in the hole disappear. So the first process where an electron goes from here to here, we call it generation of carriers. The second process where an electron from conduction band falls into the hole here, we call this as recombination. So at equilibrium, what is happening is electrons are continuously going from here, from valence band to conduction band. You have generation taking place and you also have recombination taking place. And so the two processes balance each other. Okay. So that's how, at equilibrium, we get this much concentration here. So generation is balanced by recombination. So now some of you may be wondering that you can understand that you've added donor atoms and number of electrons have increased 10 to the power 16. Why did the number of holes decrease? Maybe you can understand from here, from this picture here. Right? So now let's say you have certain number of holes here and certain number of electrons here. Say 10 to the power 10 and 10 to the power 10 here. Right? Now you add donor atoms. When you add donor atoms, what do you do to the number of electrons? You increase it dramatically, 10 to the power 16. Now what will happen to some of these electrons? They'll fall into the holes. So are you saying that the hole density will decrease now? Recombination increases and the hole density decreases here. So a consequence of number of electrons increasing here is that the hole density goes down. Okay? Because more electrons can fall into a hole and therefore number of holes will decrease here. And even if you have, let's say 10 to the power 10 electrons falling into this number of holes, it's not going to make any dent to the number of electrons here because number of electrons is 10 to the power 16. If 10 to the power 10 fall into a hole, it's not going to make any difference to electron density, but hole density will change dramatically. Okay, so this is a reason why you find that when you increase the number of electrons in the system, the number of holes goes down, and the product of P and N is always constant at equilibrium, and therefore you find the hole density becomes 2 times 10 to the power 4. So we also have a term called, in such a semiconductor, the majority carriers are electrons and the minority carriers are holes here. Because the holes are in minority, 10 to the power 4, electrons are in majority, 10 to the power 16. So that's N-type semiconductor. And what is interesting is that very small amounts of impurity, they result in very large change in resistivity. Because if you go back and look at this expression for conductivity, conductivity depends on what? Number of carriers. Right? Depends on number of electrons and holes. And I've added 10 to the power 16 impurities, number of electrons becomes 10 to the power 16. Earlier, how much was it? 10 to the power 10. So you can imagine how your conductivity will increase. Conductivity will increase dramatically because the number of electrons have gone up so much. So the point here that one is trying to emphasize is very, very small amounts of impurity can have drastic changes in the conductivity of a semiconductor here. For example, when I said I've added 10 to the power 16 electrons. Now realize that number of silicon atoms is around 10 to the power 22. 5 times 10 to the power 22 per centimeter cube. So if you look at the ratio of number of impurities that you've added, 10 to the power 16, versus the total number of silicon atoms per unit volume that you have, you find that the impurities that you've added is in very, very small quantities here. And look at the change in the resistivity. The resistivity changes in from 2 times 10 to the power 5 to 1.5 here. It's a huge change in resistivity by adding very, very small amounts of impurity here. Okay? So that's one of the unique characteristics of semiconductors, that you can drastically change the conductivity by adding very small amounts of impurity. Okay, let's come back. I'm going over it very quickly because that's just the background that we need to understand p-n junction here. P-type semiconductor, you add a group 3 impurity like boron that you see here, and group 3 impurity obviously has one less electron as compared to a silicon. And what it does is the impurity that you see here, it accepts an electron from the lattice and becomes negatively charged. And in the process, where does it get the electron? It gets the electron from the valence band. So it takes an electron from the valence band, thereby creating a hole in the valence band. Okay, so you end up getting a hole in the valence band here. So a group 3 impurity, what happens is it becomes negatively charged. We call it an acceptor impurity, and it creates holes in the valence band. Note that it doesn't cause directly any change in the electrons in the conduction band here. Okay, so if you have 10 to the power 16 acceptor atoms, what you'll do is you'll create roughly 10 to the power 16 holes. Holes will be equal to the number of acceptor atoms at, let's say, room temperature. And what happens as a consequence, the electrons go down. The electrons n and p, as I said, the product has to be ni square. Number of electrons become 2 times 10 to the power 4. And such a semiconductor where holes are majority carriers, electrons are minority carriers, we call it as a p-type semiconductor. P holes carry positive charge, so we call it a p-type semiconductor. So you have n-type semiconductor and you have p-type semiconductor. Now, number of carriers is dependent on temperature. What happens is, normally, this is where, let's say you have an n-type semiconductor, you have doped it 10 to the power 16. This is somewhere around room temperature here that you see. Okay, so you get 10 to the power 16 number of electrons in the system. If you go to very low temperature, what happens is, as I said, the electron actually came from a donor atom, right? Arsenic atom. So the electron is attached to the donor atom. Now, when you go to very low temperature, the electron doesn't have enough energy to go to the conduction band. It stays bound to the arsenic atom. And therefore, when you go to lower temperatures, what you find is, we call it as a donor freeze out, because the donor is not able to donate electron to the conduction band here. So number of carriers falls here. Okay. So you can, the reason why I'm putting this picture here is, when you make a p-n junction diode, you've created an n region and you've created a p region. It will work very well, let's say, at lower temperature, at room temperature. But when you go to very low temperatures, what will happen is the donors will freeze out. An n-type semiconductor may not remain n. We call it n because there are a lot more electrons in the conduction band. If the donors are not able to donate electrons to the conduction band, the semiconductor may not remain n. So what happens is, when you go to very low temperature, you'll find semiconductor devices will fail because the n semiconductor is losing its character. All right, donor atoms are not donating electrons to the conduction band. Similarly, acceptor atoms are not accepting the electrons from the valence band here. So what happens is, you get both donor and acceptor freeze out. So semiconductor devices will fail here. Now, what is happening so this is lower temperature. Note that we have plotted it 1 over T. So this is lower temperature. And this is somewhere like medium temperatures, room temperature, 100 degrees Celsius, and so on and so forth. Now, when you go to very high temperature, again, semiconductor devices will all fail. And what is the reason they will fail again? Because if you go back and look at this expression here, Ni. So in a semiconductor, what are the sources of carriers? One is this thermal energy is creating electrons and holes. What is the other source? The doping. Using doping, you're creating N-type and P-type, right? Now what happens is, note, suppose, just imagine for a moment, I've created an N-type semiconductor, okay? N-type semiconductor, number of electrons and holes are, let's say 10 to the power 16 here. Number of electrons and number of holes is 10 to the power 4. Okay? Now suppose I start increasing temperature. What happens? If I start increasing temperature, more and more electrons go here and more holes go here. Now can you imagine a situation where these thermally created electrons and thermally created holes, they start becoming comparable to, let's say, 10 to the power 16. Right? Because note, how does Ni increase? Exponentially with temperature. So you can imagine a situation where the number of carriers that are thermally generated, they start becoming comparable to doping. Now what happens? Number of electrons here and number of holes here will become comparable. And the material becomes intrinsic. See, remember, N-type semiconductor is what? Number of electrons here must be much larger than number of holes here. Now I'm saying the thermally generated electrons and holes become much larger than doping or comparable to doping. So the material now no longer remains N-type or P-type. Material becomes intrinsic here. So this is the picture that one is plotting here. So as I go to higher temperature, number of electrons and holes start increasing again. Why? Because of thermal generation. So again, the semiconductor here is not N-type or not P-type. It has lost its character. The semiconductor was N-type here. But if you go to very high temperature, the thermally generated electrons and holes become comparable to background doping, and therefore the material loses its character, is no longer N. So you can imagine you have a PN junction, and N is no longer N, and P is no longer P, and both are intrinsic. Obviously the PN junction diode will fail. It will not work as a PN junction diode here. Alright? So what I'm pointing out is, my material is N-type or P-type nicely in this region here. If you go to very low temperature, the carriers freeze in the donors and acceptors. If you go to very high temperatures, again, the semiconductor becomes intrinsic. It's no longer N and P. So realize that there is a higher temperature region and there's a lower temperature region. These are the two limits within which your device will work fine. Beyond that, the device will start losing its character. Okay? Alright, let's come back to current flow. Now, we've said that we have electrons here in the conduction band, holes in the valence band, electrons carry negative charge, holes carry positive charge. You apply an electric field, and obviously electrons will move in this direction, opposite to the field, and holes will move in this direction, in the direction of the field, and you get current. Whenever charges move, you get current, and I've written down expressions for current. The current obviously will depend on, this is current density, will depend on how much electric field. These equations are not really required, for further. I'm just pointing out that the current, electron current will depend on the electric field, will depend on the electron density obviously, and depends on how mobile the electrons are. Alright, so just to tell you that these are the factors here. Similarly, the whole current will depend on electric field, the whole mobility, and the whole density. These are the three factors which affect the current. And we call this current as drift current, because carriers under the influence of electric field, they drift. They start moving in the direction of electric field or opposite to the direction of. Okay, that's one. The other mechanism of current flow, which is very important also, is that carriers can move even if you don't apply an electric field. Right? If you don't apply an electric field, and if you have a lot of carriers on this side and less on this side, you know the process called diffusion. So what will happen is, if I have a lot of electrons here and less here, the electrons are going to move from here to here. They'll diffuse. And as I said, whenever carriers move, you get current. So you have another source of current which we call as diffusion current. Even if you have no electric field inside your semiconductor, if you can create a concentration gradient, then you get current flow. And diffusion currents obviously depend on the concentration gradient. This is the electron diffusion current, depends on the gradient here, del N by del X, and depends on something called diffusion constant. Similarly, the whole current depends on del P by del X, the gradient of hole density, and depends on the diffusion constant, and the minus and the plus sign because of the different charge of the carriers. Okay. So another source of current is diffusion. Keep that in mind. One source is drift. right? Because of electric field. And another one is because of concentration gradient. These two are important to understand PN junction here. Okay, so let's come to PN junction now. With this background, let's start with it. Okay, so PN junction diode, symbol all of you are familiar with. We have anode here, we have cathode here. And this is the schematic that we make, simplified schematic here. We draw a bar of semiconductor and we say this region is P-type, and we draw something in the middle. We call this the junction. And on the other side, we say it is the N-type, right? And this is where we have the junction between the P-type and the N-type. P-type is where we have the anode, and N-type is where we have the cathode here. But that's the schematic. A more accurate picture of what PN junction diode is shown over here. Okay. Now, what does this denote? This is also a schematic, but a more accurate representation. Imagine that this slab that you see here, the green slab, is a piece of semiconductor. Okay. It's a piece of semiconductor. And let's say we start off with a N-type semiconductor. The semiconductor is already N-type. Okay. Which means it has a lot more electrons and holes here. Now, what we do is we add here a lot of acceptor impurity only in this region. When we add a lot of acceptor impurity, what we can do is we can convert an N-type into P-type. We can convert an N-type into P-type because, you know, every time you add a donor impurity, what do? You increase number of electrons. Every time you add acceptor impurity, what do? You increase the number of holes. If I make number of acceptors much larger than number of donor impurity, the material becomes P-type. So, you can take a material anytime you want, you can convert it into N-type. If you want to convert it back into P-type, you add more P-type impurity. If you're not happy with it, you want to go back to N-type, you add more N-type impurity. So you can do that. Okay. So we have a, N-type semiconductor, and this region that you see here, we have created a P-type. And then what we do is we make a contact here. If we deposit a metal, we make a contact here. And this is another metal that you see here. We have made a contact here. And this would be the anode here, and this would be the cathode here. All right. And then this shaded region that you see here, we use it as to protect the device. We coat it, we cover it with silicon dioxide. Okay. So all this is silicon dioxide that you see here. So this is again a better representation of a PN junction. So when I draw a diagram like this, what am I drawing? I'm drawing actually something which is between these two lines here. Okay. This is P and this is N. I'm drawing this particular part here that you see. Okay. Okay. All right. So that's, let's come back to the operation. How does a PN junction operate? We have a P-type and an N-type. For the sake of discussion, I've taken the number of acceptor impurities as 10 to the power 16 in P-type and number of donor impurities as 10 to the power 16. So how many holes will be there in P-type? 10 to the power 16. How many electrons will be there? Just keep in mind a rough value, Ni square is 10 to the power 20. And the product of N and P is always Ni square. So if you have 10 to the power 16 here, number of holes will be 10 to the power 4. And similarly, number of electrons here will be 10 to the power 16. And number of holes here will be 10 to the power 4. Okay, so keep that in mind. Now, so this is the picture that I'm drawing here. If I look at P-type, I have a lot of these yellow circles that you see here. These are all acceptor impurities. Okay, acceptor impurities. And you can see here, they're all negatively charged. Why are they negatively charged? Because an electron from valence band has come and attached to these acceptor impurities, leaving behind a hole. So all this plus that you see here are holes. So your P-type semiconductor is like full of holes. Full of holes, and one electron that you see here, 1, 2, very few. Why? Because number of electrons, number of holes is 10 to the power 16, number of holes is 10 to the power 4. So predominantly you find there's a sea of holes here along with the acceptor atoms. The material is neutral. Keep that in mind. The material is neutral because acceptor is negatively charged and the hole is positively charged. So the whole thing is neutral. Although there are charges, distinct charges. There's something which is distinctly negative and something which is positive here, holes, but overall the material is neutral. Okay. N-type. So 10 to the power 16 and 10 to the power 4. N-type is here. Okay. N-type is all this that you see here are positively charged donor atoms, and along with that you see all these electrons here. And very few holes. You just see one hole maybe somewhere sitting there. Okay. So very few holes here, 10 to the power 4, negligible almost. and very few electrons and a lot of holes here. So imagine now that you have taken a p-type and an n-type and you've put them together. Okay, you've put them together here. All right, so now what's going to happen? Lot of holes here, lot of electrons here, very few holes. Lot of holes here, very few electrons. What did I tell you about? What are the two processes which can cause a carrier to move? Drift and diffusion. So what will happen now? I have a huge gradient. I have a lot of electrons here and nothing here. I have a huge gradient in electron concentration. And similarly, I have a huge gradient in hole concentration here. So my electrons are going to move here and my holes are going to move here. Okay, so let's make the move. All right, so let's see. There goes an electron. Once it comes to the p side, where is this electron? Where is this electron? In the conduction band. Remember all the electrons in the conduction band. Now this electron started from here and came over to the p side. Electron. And what does it find? Lot of holes. Holes are what? Empty states. So what will this electron do? It falls into the hole. Right? So this is what will happen. There. Disappear. Now, this process that you saw here, electron started from here, went over here. What happened now? You lost one electron from here and you lost one hole from here. Can you see now what has happened? This electron that you see here was sort of covering this positive charge, neutralizing it. Now, this electron is not there to neutralize. Okay? So this region, this local region has become positively charged. And what happened to this region? Negatively charged. Right? So now see the consequence. Well, a hole also will go over here. It's not, we said a lot of holes here. So the hole goes here. And when a hole goes there, what does it find? A lot of electrons ready to fall into the hole. Okay? So what will happen is there. So this process occurs and that you see here. And this will occur there. Now, as a result of which, you see that there's an electric field. Why? Because I got this positive charge here and a negative charge here and the direction of field is here. So the whole process started off with diffusion, right? And as the diffusion occurred, what happened was recombination occurred and you got only positively charged donor atoms here and negatively charged acceptor atoms here. And now there is a field. And note the direction of the field. Field goes from positive to negative charge. What will this field do? Field will prevent these holes from moving here. Note the direction of the field. The field will oppose the movement of holes here. Holes will find it now a little bit more difficult to go here. And electrons will also find it a little bit difficult to go here. But still, my diffusion gradient is very high. Diffusion gradient is very high. Field is still small, so this process will continue. It goes here, goes here. Well, I don't know how far. Okay. Now what happened? Field became stronger. Right? Field became stronger. Now you can imagine now what is happening is field will become stronger and stronger and eventually what will happen? Eventually equilibrium will be reached when there is no net flow of carriers across the junction. The two forces balance. As I said, remember there are two tendencies which cause carriers to move. Diffusion, which is the concentration gradient, and field. So what happens is, eventually the two processes balance each other and we get what we call as dynamic equilibrium. Okay? It's a thermal equilibrium that occurs here and the whole process stops. We have reached equilibrium. Okay? Now, when we reach equilibrium, what will we find? We find that there's a region here that you see close to the junction which has lost carriers. Electrons from here have gone over here. And they recombine and holes from here went over here. So this is a region that you see here. It's not that it's completely devoid of carriers, but it has lost some of its carriers here. So this region becomes positively charged. This region becomes negatively charged. And we call this region, one word for it is, phrase for it is space charge region. Makes sense? It's a spatial region where there is charge now. So we call it space charge region. We also call it very commonly depletion region. Why depletion region? Because remember this region is become depleted of electrons. Earlier it had a lot of electrons. All those electrons went away and they got lost here. So it has become depleted of electrons. This region has become depleted of holes. So this whole region that you find here has a few carriers in it, has less carriers in it. The region outside is pretty much the same. All this action that I talked about occurred here. When you go far away from the junction, p-type remains p-type. Nothing really happened to p-type. And n-type far away remains the same. All the action took place here at the junction. Okay? And we get this depletion region here. All these regions remain neutral. So you get a region here which is charged and okay. So now remember, many times what happens is a mistake commonly people make is, and this picture is also shows, it shows as if there are no holes and electrons here. Right? It shows. And many times the mistake that people make is they think depletion region means no carriers at all. Now obviously you can see that carriers are there, except that they are small in number. Note that here. If I look at my electron concentration here, we said it will be, oh, I think I've reversed it. The whole concentration here is 10 to the power 16. And the whole concentration here will be 10 to the power 4. Now, whole concentration will start from 10 to the power 16 and steadily decrease towards 10 to the power 4. Right? It will eventually become 10 to the power 4 here. Holes are 10 to the power 16. So obviously as you go into the depletion region, it will become 10 to the power 15, then 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, and eventually 10 to the power 4. So hole density is continuously decreasing here. And eventually it becomes 10 to the power 4. Similarly, when you start with electron density, 10 to the power 16 here, starts decreasing 15, 14, 13, 12 and all that, eventually becomes 10 to the power 4. So there are carriers here, but what happens is, note that if electron density is 10 to the power 16, very quickly as you get into this region, electron density, let's say, is 10 to the power 15. Okay, because remember, from 10 to the power 15, 10 to the power 14, eventually it has to become 10 to the power 4. So once it becomes 10 to the power 15, the electron density is 10 to the power 15. What is the donor density? 10 to the power 16. So number of donor atoms are much larger than number of electrons. That's why we call this region as positively charged. The electrons are not able to neutralize the donors. The number of donors is 10 to the power 16, number of electrons is 10 to the power 15 here. And then it becomes 10 to the power 14, and then 13, and 12, and 11, and so on and so forth. Okay? That's why we are denoting this region as heavily charged, and similarly this region is charged. Okay? Alright, so we call this as a depletion region. Depletion region has a dimension, has a width, and we can show that the depletion region, we can calculate the magnitude of depletion region here. How large is this region here? Depends on the permittivity of the silicon, 2s by q, depends on acceptor concentration, and depends on donor concentration, and depends on what we call as the built-in voltage, which I'll explain in a minute here. Okay, built-in voltage was not there here. Okay, so built-in voltage here. As an example, suppose I take 10 to the power 16 acceptor and donor atoms. What we find is that the built-in the depletion width is 4300 angstrom, 430 nanometer, okay, or 0.43 micron. So that's the number that you keep in mind. Depletion widths are of the order of 1000, 2000, 3000, something of that sort, angstrom. So thousands of angstrom. That's what the depletion width is, okay. Of course, it depends on, as you see here, the concentration of donor and acceptor atoms. Okay, so we can measure these depletion widths. Yes.
So what if you make a PN junction which is thinner than this?
Which is?
Thinner than this W. This is something we calculate from this theoretical formula.
Yeah.
What if I practically make a PN junction which is thinner than 4300 angstrom?
Less than 4300 angstrom. Well, no. So what happens is then things become more complicated because, as I said, there's a metal here, and there's a metal here for contact. So the metal comes in over here. Right? The metal comes in over here, and what will happen is the region between the two will be depleted. Depletion will be less. So if you make it, let's say 2000 angstrom, you'll have 2000 angstrom of depletion width. Okay. So one thing that you realize is once equilibrium is reached, you have a depletion region, and in the depletion region, as I showed, there's an electric field. Right? Look at the direction of electric field. So if I assume that the potential here is 0. Suppose, don't look at these two things for a moment. If I assume the potential here is 0, what will be the potential here? something higher because you're going opposite to the field here. So what you're noting is that the N side is at a higher potential as compared to the P side, right? And this potential is what we call as a built-in potential. It's not something that I've externally applied. It's built into my PN junction. It's a part and parcel of my PN junction, okay? So we call it as a built-in potential. Its value we can calculate. A typical value that I've shown here is 0.86 volt. So it may be 0.85, 0.9, it depends on the doping here. But note, it's not very sensitive to doping. It depends on log of doping here, not that sensitive. So a good number to keep in mind is for silicon, 0.85. 0.85 is the built-in voltage here. So between here and here, 0.85. Now obviously, this picture must be bothering you. I have ground here and I have a ground here. And then I'm saying N-type is higher than P-type by 0.85. It looks like a contradiction here, okay? Now this is not the complete picture. What you have to carry in mind, I'm talking about now something very general. What did we find? We said that when you take a P-type semiconductor and an N-type semiconductor and you put them into contact, right, there's an exchange of carriers and a voltage develops. And the voltage is what we call as built-in voltage. Now, I'm making a very general statement. Anytime you take two different material, you put them into contact, what happens? A potential develops. Because there's an exchange of carriers and a potential develops. So a very general statement, anytime you put two things into contact, you have what we call as contact potential. You have contact potential. So PN junction, this built-in voltage is nothing but contact potential. Alright? So anytime you take copper and aluminum, you put them together, there will be some contact potential. Okay? So that's a very general statement. Now, this picture is not complete because remember, we have taken P and N type, but how do I connect something to ground? I have a metal. I have a metal here and I have a metal here. So let's look at the complete picture here. I'm not going to go into the details, but you can see here, contact potential between P and N type is like this, 0.86. We said N type is higher than P, 0.86. Now, between N and, let's say this is a copper wire. So between copper wire and N type, what will I have? A contact potential again. Okay, a contact potential. As I said, anytime you put two things into contact, you have a contact potential. Let's say it's 0.21. Now, between P-type and copper wire again, you have a contact potential. Now, P-type is different and N-type is different, so contact potentials are different. You have 0.65. And now, of course, you're taking the copper wire and connecting it together, right? They're shorted together. Now you see that they add up to 0. There's no problem. Okay, there's no problem that N-type is higher than P-type because there's a potential drop here also between N-type and the copper wire here. And there's a potential drop here also between P-type and a copper wire here. And all the potentials add up to 0. This also tells you that if I connect a multimeter here between this wire and this wire, what will I measure? I'll measure 0. So that's why you can't simply take a PN junction diode, connect a multimeter and hope to measure the built-in voltage. You'll never be able to measure. Okay, because of this cancellation that will always occur. Okay, which will always occur here. All right, but there is a built-in potential here. All right, so this very important PN junction feature of PN junction is the built-in potential here. All right, let's come back to the operational aspects here. We say so now. I have said that there's a built-in potential here. There's a built-in potential here, but we make the contacts in such a way that my contacts are transparent to carrier. Meaning what? An electron, even though there's a built-in voltage, a built-in potential between these two contact potential that you see here, the carrier from here and here, it can go freely. We make the contacts in such a way that the carrier can go across the contact into P-type and from P-type to the contact very easily. We call such contacts as ohmic contacts. So similarly, we make the contact here so that this carriers can freely go and move back and forth here. Okay, so that's why the behavior of the PN junction is not determined by the contacts here. They don't bother you. The carriers can go freely across. What determines the behavior of the PN junction is this part here, the junction here. Okay, it's not determined by the contact. That's how we make it. If you don't make it properly, then what will happen is this will start bothering you also. Current will get limited by this junction here, will get limited by this junction here, as well as this junction here. and PN junction will no longer have its unique characteristics because it's being determined by now 3 junctions. But we deliberately make it such that this junction is like transparent to carriers and this one is also transparent to carriers. Okay, forward and reverse bias, all of you know. The way you forward bias it, you make P-type more positive than the N-type. And the way you make it reverse bias is you make it N-type more positive than the P-type. And you know that. And when we make forward bias, you also know that this is the picture that we get. These are the measured characteristics of 1N4001. And we find this is plotted on a linear scale. So it's appearing as if it's all 0 here. It's not 0, it's some low current. And this is the picture that you have. In forward bias, you find diode conducts current, significant current. And in reverse bias, it does not conduct current. It does not conduct significant current. Okay, the important word is significant. There is some current, but it's very small as compared to the forward bias current here. So we know that. The issue is why. Why does that happen? Okay. All right. So let's look at forward bias here. We all agree with this picture of PN junction. There's a depletion region. Outside, there's an N region here with a lot of electrons. And there's a P region here with a lot of holes. How many holes are here? Very few. How many electrons? Very few. Now, I'm forward biasing it, right? I'm applying a positive voltage here. When you apply forward bias, now positive voltage, what happens is, this voltage that you see here, internally, what do I have? I have some built-in voltage. I have inside some voltage here. Now, I've applied an external voltage here. What will this external voltage do? As I said, the contacts are transparent. So this voltage doesn't get dropped here. This voltage straight away goes here. And what will it do to my field? It will decrease the field here. Why? Because it opposes. It opposes the original field here, so the field becomes smaller. All right. Now note that when you apply a positive bias here to the P side, in which direction do you want current to flow? Here, right? This is the direction of current to flow. When you apply a positive bias, you're asking current to flow from left to right. In which direction should holes flow? If the current is in this direction, holes should flow in this direction. In which direction are you asking electrons to flow? Opposite. It makes sense. You're asking the right thing to happen. There are a lot of holes here, right? And you're asking holes to go from left to right, which is fine. And there are a lot of electrons here. You're asking electrons to flow from left to right. That's also fine. Earlier, they could not flow. Why? Because the field was opposing it. Now I have reduced the field. So what happens is diffusion will push the electrons from here. Diffusion now takes an upper hand because you've reduced the field. So diffusion will push the electrons over this side. Holes will go over this particular side. And you know now current will begin to flow. Okay. So application of forward bias lowers the built-in potential. Now inside, what will be the potential inside? It will be the built-in potential minus the potential that you applied. Okay. That's what will happen. So application of forward bias lowers the built-in potential and allows holes and electrons to cross the junction and result in current flow. Okay. So this is a picture which tells you that earlier the built-in voltage was like this here. Now what happens is you reduce the voltage from original VBI to VBI minus VF. VF is the forward bias here. And when you reduce the field, what you also do is reduce the depletion region. Because the size of the depletion region is directly related to the field. So when you reduce the field is resulting from charge, so you reduce the depletion width here. So the earlier depletion width was this black lines that you see here. Now these red lines here that you see here. Depletion width becomes smaller, current begins to flow. Okay. All right. Let me stop here because I have only 1 minute to talk about this one. So let me stop here. And the tutorial tomorrow, as I said, we don't have it in the tutorial block. We'll have it in a lecture room. I don't have it where I'm going to hold it. So I'll send an email. Please watch out for email. By evening, I'll tell you where the room is. Okay. So we'll have, and I've circulated the homework assignment. Go over the problems. First 10 minutes, we'll have a mini quiz based on the homework assignment. Okay. So we'll have it. Okay. So be prepared. Okay.